Not sure if you've ever noticed, but when you walk around campus and you look at the edges of the buildings, you'll see these plastic boxes that are sitting at the edge of the buildings. And this is true for pretty much any commercial building here in Southern California. And so let's go ahead and talk about what those plastic boxes are for. And what got me thinking about these plastic boxes was a news article that I saw that came up in my Google News feed that was talking about a case report for a medical incident. And it starts off by saying, a 30-year-old man came to the emergency department with right lower quadrant abdominal pain. The pain was sharp, burning, constant, radiating to the right flank and associated with nausea and dark brown urine. His past medical history was positive for polysubstance abuse, including cocaine, K2 spice, and alcohol abuse. Now, I'd heard of cocaine and alcohol, but K2 spice was something new to me. And it continues on by saying the patient was homeless, unemployed, and living with his girlfriend. It explains later in this article that this K2 spice is a type of synthetic marijuana, means it's just some sort of leaves that they have impregnated with cannabinoids, synthetic cannabinoids that are very powerful, more powerful than the THC that you find in marijuana. But it says that this version that you can buy is laced with many agents, including brodi-fa-coum, which increases the euphoric effect by slowing its metabolism. And that is interesting and disturbing. Let's go ahead and talk about this molecule brodi-fa-coum. And where would you find brodi-fa-coum? You would find brodi-fa-coum in those plastic boxes. Those are rodent bait stations that are designed to kill rodents like rats. Brodi-fa-coum is an anticoagulant that stops clotting, blood clotting, and so basically the animal will bleed to death from the inside to out. If you look on Wikipedia, it tells you that brodi-fa-coum is a highly lethal anticoagulant poison. It has become one of the world's most widely used pesticides. If I'm not mistaken, its use was discontinued in California just a few years ago because it's very powerful. Where do you get brodi-fa-coum? You synthesize that. It's not a natural compound. You synthesize that using a Friedel-Crafts, intramolecular Friedel-Crafts acylation reaction, like the kind of reactions that we've talked about in this class. This bond right here is made using an intramolecular Friedel-Crafts cyclization, and then you do an extra reaction to make a CC bond with the resulting ketone. They take this here's one supplier that sells brodi-fa-coum in this kind of feed right here, and you stick that onto wires in those boxes so that the rats and mice can't carry that stuff away from the box. And this is what has been put into this K2 spice ingredient thing. And why is that legal? It is legal because on the back of the packages they say not for human consumption. But that's the obvious intent of them selling that. You know, the thing that's profound about that article, about this medical case history, I don't think was really so much the brodi-fa-coum. To me, it was the fact that there was some woman that was letting this dope-smoking homeless boyfriend live with her. And it got me thinking that what should she be telling her boyfriend? We ought to have some sort of a Kahoot poll saying what she ought to be telling her boyfriend. One thing she could tell her boyfriend is, hey, why don't you move in with me? Maybe then you won't be homeless. Alternatively, she could just ask him, stop bleeding all over my couch. Or maybe it's your fault for buying the cheap stuff instead of some expensive brand of synthetic marijuana. Or maybe she could just conclude, hey, kills rats, huh? Well, it seems to be working on you. Let's go ahead and continue off. Let's go ahead and continue off where we left off. Let's go ahead and continue off where we left off on our lecture on Wednesday. I was introducing to you a strategy for approaching spectroscopy questions. Spectroscopy questions and the use of spectroscopy is all about eliminating possibilities. You use spectroscopic data to rule out possible structures so that you're only left with the correct structure that is consistent with the spectroscopic data. Sometimes I give you a list of structures, that's easier. Sometimes you have to generate the list of structures by knowing the possible products of the reactions. Well, maybe it's an E1 reaction or an E2 reaction or an SN2. Let me draw all those products out and see which ones I can rule out using spectroscopy. And the basic strategy is to use the easiest spectroscopic data first. That's almost always, if it's given to you, the molecular formula, which you get from mass spectrometry. And then I told you the second easiest piece of spectroscopic data for you to use, if you've got it, is carbon-13 NMR spectroscopy. And you may be saying, well, I don't really know that much about carbon-13 spectroscopy. So I tried to give you a basic outline of carbon-13 spectroscopy and why it's useful. First of all, it doesn't have all that splitting in there. That singlet, triplet, doublet, thinking about neighboring protons is so confusing. Without that splitting, you just count up the number of peaks in the carbon spectrum, and that's how many unique carbons, without taking symmetry into account, you should have in your chemical structure. And counting carbon peaks is a pretty easy thing for you to do. The other thing that's useful about C13 spectroscopy is that the chemical shift ranges are highly modular, right? You can know how many singly bonded carbon atoms there are in your structure just by counting the number of peaks that are below about 110 ppm, and that should match the number of singly bonded carbons in your structure. The C double bond C carbons are localized into a really specific range. And if you have 6 peaks in that range, it is probably not 3 double bonds. It could be, but it's probably just going to be some kind of a benzene ring that is not symmetrically substituted. And then carbonyls, the other advantage of carbonyls is you can tell the difference between ketones and aldehydes versus esters, amides, and acyl chlorides. And that's not so easy to do with an IR spectrum that just kind of tells you there's some kind of a carbonyl in there. So C13 is super useful. I usually go to that first if I'm just looking for an easy way to rule out possible structures. All right, so what are one of the key things for this chapter, because we're learning how to condense reagents with carbonyl groups. Condense means you lose water as a byproduct. We're learning how to condense things with carbonyl groups, and we need to know how to make ketones and aldehydes. This chapter focuses on ketones and aldehydes. And so the book starts you off by making sure that you know how to synthesize ketones and aldehydes from other functional groups. So let's go ahead and review some of the ways to synthesize ketones and aldehydes, because I will ask you multi-step synthesis questions. I'm going to ask you multi-step synthesis questions in the discussion section. I'm going to ask you multi-step synthesis questions on my exams. And so you need to know how to make ketones and aldehydes and convert them into other things. So the first reagent that you should know for making ketones and aldehydes is PCC, pyridinium chlorochromate. Came from the chapter on reduction and oxidation reactions. You don't have to know the chemical structure in my class. That would be great if you learned it, but you don't need to know it to be able to use it for this transformation. So that's a valuable way to take primary alcohols to aldehydes and stop right there at an aldehyde, or to take a secondary alcohol and convert it to a ketone. So, and then once you do that, you can add Grignard reagents to the carbonyl. You can do all these chapter 18 reactions to the carbonyl. So you need to know that. Now in the last chapter, I showed you a bunch of hydrido reagents, lithium aluminum hydride, sodium borohydride, and we introduced a reagent that didn't get a very large section of the chapter devoted to it, but it's quite powerful for this one transformation. And that is converting esters to aldehydes. And there's not an exactly one step, but this is the closest you can get to a one-step way to do that reaction. So step 1, you use dibal-H. It's an aluminum reagent that is very different in structure and in mechanism from lithium tetrahydridoaluminate. I didn't show you the mechanism. I don't think the book shows you the mechanism for this, so you don't need to know it, but you need to know dibal-H. Step 2, it's going to be a water workup, as we've frequently seen. And in this case, the water workup is actually for protonating the alcohol leaving group. So there would be another leaving group. And usually, almost always, that's ethanol and methanol, and we evaporate it away and get rid of it. But that's what the workup is for. So usually we don't care about the ethanol or methanol part. We're almost always just trying to take some big thing and have an aldehyde sticking off the end of it. Now, way back in your book, right after you talked about alkenes, there was an entire chapter on alkynes. And we showed you how to do hydroboration oxidation reactions of alkenes. And then we said, oh, but with alkynes, something slightly different is going to occur. You don't end up with an alcohol product. So let's go ahead and review what are the conditions for hydroboration oxidation. You need to know this. So we've shown you how you can take alkynes and add the acetylide anions and add them to carbonyl groups. So once you do that, you can take that alkyne, in this case if it's a terminal alkyne, and do hydroboration oxidation. Step 1, borane, BH3. Now step 2 is kind of hard to remember. It had a bunch of stuff in there. The real reagent is sodium hydroperoxide, but you can't buy that, at least as far as I know, or maybe it's too expensive. So we make sodium hydroperoxide in the lab by dumping in sodium hydroxide, and then we add to that hydrogen peroxide. You can buy both of those at your grocery store. Sodium hydroxide is used as drain cleaner, and hydrogen peroxide comes in brown bottles as a disinfectant. Sodium hydroxide and hydrogen peroxide. So you can see here you had one H on there, you still have one H on the end. So if it's a terminal alkyne, you get good selectivity. If the alkyne is in the middle of a chain, you're going to end up with a horrible mixture, and that's not really that great. So this is most commonly used if you have a terminal alkyne with a CH at the end. Now another reaction that you covered in the reduction oxidation chapter was how to cleave CC double bonds using ozone. So this bond right here, you can cleave using ozone to make 2 carbonyls. And that can allow you to make ketones and aldehydes. So step 1, here we're going to use ozone. You don't need to know the Lewis structure for ozone. It would be great if you knew the Lewis structure, but you don't need to. And then we have to work this up. You know, when you're done with these reactions, there's a lot of dangerous peroxides floating around in your reaction mixture and attached to your ketone products. And we have to reduce those dangerous oxygen-oxygen bonds. That makes things explosive. Weak oxygen-oxygen bonds want to explode. And so we have to reduce this using a reagent dimethyl sulfide. I usually write it out like this. I usually write it Me2S. So it's a thioether. It's like an ether, but with sulfur. And this is probably the cheapest, most readily available one. The byproducts from that sulfur are easy, you can evaporate off. So you can cleave CC double bonds to give carbonyls using ozonolysis. So you need to know these methods for making aldehydes in this case. So now let's go ahead and review some methods for making ketones. Some of them overlap, some of them it's the same idea. Let's go ahead and take a look at that. Okay, if you have a secondary alcohol, an alcohol with 2 now you have to have an H on there. This H is essential, right? Because you can't oxidize if you don't have that H there. And what's the easiest reagent to remember here? It's still PCC. PCC is total money. You need to know that reagent. It's so easy to remember, and it's so valuable for making aldehydes and ketones so that you can do Grignard chemistry and alkylithium additions and all this chapter condensation reactions and more reactions that we're going to cover in the next 4 to 5 chapters. Now there's another reaction you know for how to make ketones that we started off with, and I'm realizing this chapter number is actually not accurate. That should be 16.5 in the 6th edition of our textbook. 18.5 was a previous edition. So this is Friedel-Crafts acylation. Boy, I hope you all know Friedel-Crafts acylation because our first exam covered that. And remember the Lewis acid catalyst that you used for Friedel-Crafts acylation? It was aluminum trichloride. So that's a valuable way to make ketones. And once you make a ketone, you can do all these chapter 17 and 18 reactions using that ketone. Now I just told you about ozonolysis, right? That you can use the same ozonolysis reaction to make ketones, like this one right here. Just depends on the substitution of your alkene. So what are our conditions for ozonolysis? Step 1, ozone, O3. Step 2, We use that sulfur reducing agent. It's a sulfur ether, and it's the smallest one you could think of. Dimethyl sulfide or dimethyl thioether would be two ways to describe that. Now, the last reaction for making ketones, I've never known anybody to use this reaction ever, but the book tells you about this, and it's adding a cuprate to an acyl chloride. You forget that. I'm never going to ask you that. That's dumb. Okay, so you got some powerful ways to make ketones, and you need to know how to make ketones and aldehydes and then do more reactions with them. So let's go ahead and start talking about ketones and aldehydes and adding more reagents to them. And I want to try to put this chapter into perspective with the kinds of reagents that we learned about in the last chapter. Now, in the last chapter, we talked about powerful nucleophiles that we could use: carbon-lithium bonds, carbon-magnesium bonds, acetylene-sodium bonds, where the carbon is super nucleophilic, and you can use those types of powerful reagents for making carbon-carbon bonds to carbonyl groups. So you get these, right? You get a new powerful carbon-carbon bond, and I'm all about making carbon-carbon bonds because I'm an organic chemist. And you end up with these intermediates that'll just sit there. They just sit there and sit there and sit there until you work up the reaction by doing some sort of an H2O workup. So you come along, dump a bunch of water in there. This is really just an equilibrium reaction. You're driving the equilibrium by adding a ton of water, and you end up with an alcohol. Now, you don't need anything special to get a carbon-lithium bond to add to a carbonyl. Right? A carbon-lithium bond is so powerful. It'll add to CO double bonds. It'll add to CN double bonds. We haven't really talked about that. But in this chapter, we're going to talk about some nucleophiles where they just don't easily add to carbonyl groups. And in particular, the one that's really going to stick out for us here are alcohols and water, OH groups. You know, they have a lone pair on that OH, and it is definitely true that an alcohol will add to a carbocation. And it is definitely true that water will add to a carbocation. But they will not add at good rates to ketones and aldehydes. So in these cases, we generally want to have some sort of an acid catalyst in there. And this is going to be completely hard to I think, to understand. Like, why would we want to put some sort of a catalyst in here? You need a catalyst. That's supposed to be just a simple A symbol there. You need an acid catalyst to get OHs to add to carbonyls at decent rates. Oxygen, alcohols, I'm not talking about O-, but neutral OH is just not really nucleophilic. And the trick is, you might be asking, well, won't the alcohol just protonate the OH? Yes, it will, but it's reversible. And every once in a while, the acid is going to protonate the carbonyl group. We're going to see protonation of the carbonyl group, and it's going to superactivate that carbonyl group. So when you've got OH nucleophiles, you really have to, you have to protonate this carbonyl and turn it into a super electrophile if we want alcohols to add to this. So now that carbonyl is not just a regular carbonyl, that is a super electrophilic carbonyl, and even a pathetic nucleophile like an alcohol can add in, or water can add in at good rates to this protonated carbonyl. We don't have a great name for this protonated carbonyl functional group. Anytime you have oxygen with 3 bonds, you call that an oxonium ion, right? H3O plus is an oxonium ion. It's got 3 bonds to oxygen. So this is an oxonium ion, but it's not 3 single bonds. It's 1 double bond and one single bond to the H. Now all of this is in equilibrium, right? You protonate the carbonyl, you take the proton off. You protonate the carbonyl, you take the proton off. And then every once in a while, this alcohol will add and form a bond to that carbonyl. And we're going to see this in this chapter. We're going to be seeing addition of nucleophiles under acidic conditions. And there is no way you could have done that in the last chapter when you're adding alkylithium reagents and granules. In this case, with alcohols and water, we're going to need to have acid present in the presence of this weak nucleophile. And then this, mechanistically, This is so unstable, it'll keep doing other stuff. Okay, so this chapter is weird. We're going to have acids present or potentially acidic species. OHs, we can have OHs present with the nucleophiles, and we couldn't do that last chapter. That's why we had to enumerate the steps. Step 2, then you add the water or the OH compounds. So let me try to distinguish some classes of reagents based on whether you can have acidic OHs present or acid present versus you have to keep them away, absolutely keep them away. Okay, so I've tried to group up the kinds of nucleophiles that we're going to see here in Chemistry 51C, maybe that you might have seen in other chapters like that sodium acetylide. And let's talk about whether you can have acidic protons present in those reaction conditions and how that relates to the mechanism. So we just finished a whole chapter, chapter 17, where we talked about hydridoaluminate reagents, super powerful nucleophiles. Hydridoborate reagents, very powerful. And then amazingly nucleophilic carbon-magnesium bonds, carbon-lithium bonds, carbon-sodium bonds. And the nucleophilicity of carbon-magnesium, carbon-lithium, carbon-sodium is not so much dependent on the sodium or lithium or magnesium. It depends on the hybridization of this atom, the carbon atom, whether that carbon atom is sp hybridized, sp2 hybridized, or sp3 hybridized. You can see here that corresponds to a difference of 25 orders of magnitude, the hybridization of that atom. If you have not been looking at the hybridization of carbon, nitrogen, and oxygen atoms, you've been missing this huge span, this huge dynamic range of reactivity. So there's a huge difference in reactivity between sp3, sp2, and sp atoms. That's a concept we'll come back later and talk about when we talk about the basicity of nitrogen compounds. So all of these nucleophiles, including alkoxide anions, those we will see, and we've already seen, that they can add to carbonyl groups with no assistance. Right? Those nucleophiles are so nucleophilic that the nucleophile can simply come in and add, whether it's a bond or a lone pair. And as long as we keep acidic protons, OHs even, out of these reaction conditions, we can successfully make bonds to carbonyl groups. So under these conditions, we avoid acid, even OHs, right? If you want to protonate your O- product, you come in as a second step. At the end of the day, when all your bond formation's done, then you put in the OH, the water, to do the workup. So this has been really the theme for the past chapter. This is mainly chapter 17 stuff and alkoxide chemistry. If you've covered that, you would never take sodium or potassium T-butoxide and dump hydrochloric acid in there, because that's just going to ruin your reagent. Okay, but let's talk about what we're going to see in this chapter. In this chapter, we're going to introduce you to two nucleophiles that are not powerful nucleophiles. They are weak nucleophiles. Maybe depending on the chapter, somebody might get proud and call them strong nucleophiles. But these are relative to organometallic reagents. These amines are weak nucleophiles, right? Amines. And then we're going to talk about a nucleophile, cyanide anion, right? It's sp hybridized and it has an electronegative nitrogen attached. That is a weak nucleophile. Look, in orders of magnitude, nucleophilicity, how much weaker it is than carbon-lithium bonds or carbon-magnesium bonds. And we use these reagents, to great surprise here, we use these reagents under reaction conditions that are weakly acidic. Wow, that's surprising. I mean, you can never tolerate any kind of acidic conditions for alkylithiums. No way. So it's going to be surprising to you in this chapter that we're going to have weakly acidic conditions. And the reaction still involves nucleophiles adding to carbonyls, but you have to have that acid in there, and we'll explain mechanistically why that's true. Now let's talk about the last category of nucleophiles that we're going to talk about in this chapter that add to carbonyls, and that's alcohols and water. And I just told you, if you want an alcohol or a water to add to a carbonyl group, you've got to figure out how to get a proton on that carbonyl group, or you are not going to get alcohol or water. I'll just kind of symbolize it as ROH. You're never going to get this OH to attack at decent rates, at acceptable rates, unless you've protonated that carbonyl. So if you want to get alcohols and water to add to carbonyls, we really need to do these under acidic conditions. And I'll write strongly acidic conditions, because that's the, if you're trying to do this in a synthetically useful manner. then you're going to find yourself adding strong acid in the presence of your alcohol nucleophile. Okay, so this is kind of trying to give you a roadmap or maybe a chart, a way to think about chapter 17 chemistry, which is organometallic reagents, and then here in this chapter where suddenly we're putting acids in with our nucleophiles. It may seem odd, but there's a, right, the reason we do that is because there is a massive, massive difference between the kinds of nucleophiles you learned about on top here in the previous chapter versus the kinds of nucleophiles we're going to be talking about in this chapter. Those are hugely different types of nucleophiles, right? And if you just look at this rank order log scale reactivity, you get a sense for the breathtaking differences in nucleophilicity. Let's go ahead and talk about our first reaction here for the chapter. It does not fit in. It just got thrown into this chapter because I'm not sure why it got thrown into this chapter. It's not a super important reaction. And it is not a condensation reaction, so that's why, to me, it doesn't really belong. But it is one of these weird nucleophiles where you do it under acidic conditions. Let's go ahead and take a look at this reaction. There's a reaction for adding cyanide to carbonyls, to ketones and aldehydes, to make carbon-carbon bonds. So if I take an aldehyde, what I need to do is I need to add hydrocyanic acid, HCN. But you can't easily buy HCN. I suppose you could buy a gas cylinder of hydrocyanic acid, which nobody wants to deal with that. Nobody does that. We make that in our laboratory. We take sodium cyanide powder or pellets or something. Right? It's easy to weigh out on the balance. Doesn't kill you. Just you could touch it and you wouldn't die. I'm not saying you should touch it ever, but and then you take that powder and you put it into hydrochloric acid. And that makes HCN. It makes HCN under the conditions of the reaction. So, so these conditions right here are just making HCN. You're protonating the cyanide anion. So could you buy some HCN? In theory, but don't write HCN because we're not teaching you HCN as a reagent. Okay, and what you get is a new carbon-carbon bond. Let me go ahead and draw out the product here. The product has a name. It's called a cyanohydrin. And it's got a carbon-carbon bond right there and a cyano group attached to that. But be careful. You should notice that, let me go ahead and write out the name of this. It's called a cyanohydrin. It's in the title of the slide. So if I say cyanohydrin, it's this particular functional group right here. And it's got a carbon-carbon bond. But note, we've just generated a new stereogenic center. That cyanide anion can add from the top face of that aldehyde or from the bottom face of that aldehyde. There's two different faces to that aldehyde carbonyl group. And you're going to get two different stereoisomers out of this, mirror images. I guess I can make any of these bonds, these bonds here, a wedge. I'll draw the H going backwards. So if the cyanide adds from the top, you'll get that. You know, half of the cyanides add from the top, the other half add from the bottom and give you the mirror image. So if I draw a box and say draw the product in the box, I expect you to show the stereochemistry in the presence of stereoisomers like the enantiomer, if you want full credit when I say draw the product in the box. So again, it doesn't look dramatic, but you just formed a carbon-carbon bond. All right, let's go ahead and take a look at what's happening mechanistically. Maybe it's obvious what's happening mechanistically. You've got some sort of an aldehyde or a ketone in here. Could be, you know, R could be phenyl, R could be methyl, R could be H, you know, it could be any sort of H or carbon group on here. And cyanide is not a super powerful nucleophile, but it is nucleophilic enough under the conditions of the reaction to add to the carbonyl group. So notice we're not using the acid yet. Yes, the reaction is in hydrochloric acid, but you don't use acid in the first mechanistic step if you're drawing out the arrow pushing mechanism. So we're using acid here in the next step of the reaction. So now we've made this carbon-carbon bond. I'll draw the cyanide going down here. And now the conditions are acidic. Something in there is going to protonate this alkoxide intermediate here. And you don't know what's going to protonate that alkoxide intermediate. What's protonating it? Is it the HCl or is it the HCN? You have no way to know. That's why when we draw arrow pushing mechanisms, we often, I would encourage you to draw out a symbolic acid that's sticking the proton on there, because nobody, you or me, knows whether it's an HCN molecule or an HCl molecule that is sticking the proton on there. And so that's why we tend to favor these symbolic acids if we're under acidic conditions, and if we're under basic conditions, we do proton transfers with the symbols HB and B. You just have to decide whether the conditions are acidic or basic. All right, so this is what leads to this cyanohydrin functional group. It's got a brand new carbon-carbon bond in there. This is an arrow pushing mechanism, so don't worry about the stereochemistry on this. All right, that's a cyanohydrin. Now, this is an equilibrium process. I'm not going to draw the equilibrium arrows. It turns out if you add base to a cyanohydrin, it'll go backwards and push out the cyanide anion. So you can't run these without the HCl. The HCl is not just important for the mechanism, but it ensures that the equilibrium lies on the side of the cyanohydrin adduct. Now, we're going to show you, the book shows you a reaction that is a useful reaction of cyanohydrins, or actually it's a useful reaction of any cyano group. And we're going to have a whole section of chapter 19 is going to be talking about the reactions of cyano groups. So if I make a cyanohydrin, let's suppose I take cyclohexanone and I do my conditions for cyanohydrin formation, sodium cyanide, hydrochloric acid. Right? That's the way we do it in the lab. Sodium cyanide and hydrochloric acid. And that will make a cyanohydrin with that new carbon-carbon bond in there. So easy. It's like the easiest carbon-carbon bond. Now, nobody really wants that cyanide group on there. There's a few pharmaceuticals that have cyano groups on them. I'm trying to remember, there's a common antidepressant, and maybe it's, I don't think it's Paxil, I can't remember which one, that has a cyano group on there, but usually nobody wants the cyano group on there. And so we want to change that cyano group into something we do want, a more common functional group. And one of the most common functional groups is a carboxylic acid. So I'm going to show you conditions for changing that CN triple bond into a carboxylic acid. And it doesn't matter, the cyano group can be directly attached to a benzene ring, the cyano group can be on the end of a long alkyl chain, the cyano group can be on the other side of the universe, as long as it's still in your reaction. I don't know how that would be. But we can change cyano groups into carboxylic acids, and that's the functional group you usually want. And the way we do this is with powerful acid. Actually, I'm just going to write it out the way I would expect, the minimum way I would expect you. I was going to write out the concentration, which is typically 6 molar hydrochloric acid. That is concentrated. You need concentrated acid to hydrolyze a cyano group. This is the most common set of conditions: HCl, H2O, and heat. Heat means you boil it overnight. Right? Most of the reactions we do in the lab, we want it to be done in an hour, but that's not long enough. You need powerful concentrated acid, dangerous levels concentrated water, and you need to boil the heck out of it. It's hard to do this type of hydrolysis. We'll see more of these types of difficult hydrolyses, specifically of amide bonds and peptide bonds like given proteins. Hard to hydrolyze. They take these crazy conditions, boiling 100 degrees Celsius overnight. Now, I'm not going to show you the mechanism for this reaction. I've indicated down below. It's a 12-step mechanism, and I'm never going to ask you a 12-step mechanism on my exam because I don't want to grade a 12-step arrow pushing mechanism on the exam. I wish you would take the time to learn that mechanism, but it's just not going to be worth our time here. And we're going to cover similar types of arrow pushing mechanisms individually when we get to chapter 20. So I'm not feeling bad about skipping the mechanism for this right now. But you need to know that transformation. All right, so cyanohydrins. I told you I was going to give you like 5 recipes or something. We just finished the first one, cyanohydrin formation. Let's talk about the second powerful recipe, and that is taking CO double bonds and converting them into CC double bonds with a single step and a single reagent. And you're going to do something similar to this if you're taking the Chemistry 51C laboratory. So we're going to show you how to take bonds like this, CO bonds like this, and convert them into CC bonds like this. That's useful. You've got a whole chapter of reagents that you can add to CC double bonds. You can add HBr across double bonds. You can do acid catalyzed hydration of double bonds. That's all Chemistry 51B stuff from chapter 10. So it's valuable to take carbonyls and convert them into CC bonds. You could add HBr to that and then convert that into a Grignard reagent. Like the number of transformations you have at your disposal is going to rapidly explode, which is great. It gives you the power to make cures to cancer, cures to diabetes, diagnostic reagents, smart materials. The problem is you got to keep track of all these reagents and practice with them. So that's the downside. It's powerful, but you got to practice using them. Let me show you the secret reagent here. The secret reagent is called, that we're going to teach you about, is called a Wittig reagent. It's a phosphonium ylide reagent, which is going to blow your mind. In the laboratory, you're going to use a slightly different phosphorus reagent. And what's going to blow your mind here is I'm going to draw phosphorus with 4 bonds and a positive, and then right next door, I'm going to draw a negative carbon. That means there's clearly a lone pair on there. And you're probably saying, well, if there's a lone pair right next to P+, why don't you just make a double bond instead of leaving those 2 charges? Isn't this thing aching for you to attack the plus using the minus? We'll talk about that later. But just draw it like this for now, because this way it reminds you the carbon is nucleophilic. Right? That's the advantage of spending all this time to write all those pluses and minuses. The lone pair is optional, but I like to see that on there. Now, again, we call this a Wittig reagent. Let me just write that down here. And this is called a Wittig reaction or a Wittig olefination reaction. And Wittig won the Nobel Prize for developing this reaction. Now, full disclosure here, and this is kind of a pain. It makes me not want to ask about this. So I have to be very careful to design questions with this, because you get 2 different stereoisomers. And I tell you in this class, clearly indicate stereochemistry and the presence of stereoisomers. And if you're watching here, I just formed one of 2 possible stereoisomers. Not R and S, but Z and E. Remember, alkenes can exist in 2 different configurations depending on the substituents. And what I've drawn over here has the R group opposite the ethyl group on the other carbon. That means it's the E isomer. E meaning German for entgegen. So that means there's another isomer, the cis or Z isomer. E and Z are the IUPAC descriptors. And the relationship between the R and the high priority group, the ethyl group, those are cis to each other. But by IUPAC, that's the Z isomer. So to get this correct, you would have to draw both of those compounds. If I said, what's the product of this reaction? I tell you, clearly indicate stereochemistry and the presence of stereoisomers. And alkene isomers, E and Z, are isomers that you have to keep track of. I hate keeping track of that, and that makes me not such a big fan of the version of this reaction they show you. There's another byproduct of the reaction, and it is the main driving force for this reaction. And I'm going to go ahead and draw out the byproduct, even though we always throw this away. Nobody has ever wanted to keep this. Unfortunately, it sometimes contaminates your other stuff, and you spend days trying to separate it out. It's called triphenylphosphine oxide. Look at this. It's got 5 bonds to phosphorus. Isn't that crazy? No. That's just like DNA and RNA. Every single nucleotide subunit in DNA and RNA has 5 bonds to phosphorus. Phosphorus is in the 3rd row. It's not a 2nd row atom, so of course it can have 5 bonds. It can have a double bond and 3 singles, or 5 single bonds. That's less stable. So we call this triphenylphosphine oxide, and that PO double bond that didn't exist before is super stable. Nature makes nucleotides, oligonucleotides, out of P double bond O functional groups because those are so stable. So this is the driving force. You can do whatever you want in the reaction, but if you're forming P double bond O, man, that's going to be a strong driving force for that reaction. Okay, so that's called triphenylphosphine oxide, and that's what drives the reaction. Let's take a look at some applications of this. How do I get around this thing where you form 2 stereoisomers? I don't ever in my life want to set up a reaction and get 2 of anything. When I go into the lab and I run reactions, I want to get one product. Because if you have two products, you have to purify them out. That can take more, that always takes more time than setting up the reaction. Any dodo can just pour stuff into a reaction flask. All your time and effort in organic chemistry is spent purifying stuff, separating things apart. So how do you use Wittig reactions so you don't end up with two stereoisomeric products, two E and Z products? Well, one trick is to take ketones that are symmetrical, where the group on both sides of the carbonyl are the same. You won't end up with an E and Z situation if both of those groups are the same. So if I take my Wittig reagent, let's go ahead and draw that out. pH3. Boy, when I was an undergrad in your stage, I always used to get confused about these P's. It's like, which P has the H and which P is the phosphorus atom? I don't know if you'll get confused by that like I was. It's like half the time I would write it out wrong and then lose points, like you will lose points. Like if you write P3PH, that's wrong. You gotta put the H. It's 3 phenyl groups attached to a phosphorus atom. So you might be wondering, why don't I draw out the phenyl groups? I don't have the room for that, unfortunately. So there's no room for me to draw those 3 phenyl groups attached to the phosphorus. Trust me, this is better. You can barely see it, but there's a plus here on and a minus charge there. So if I do a Wittig reaction on a symmetrical ketone, I'm going to end up with a product where there's no such thing as E and Z, because the phenyl is always going to be next on the same side as the methyl group, no matter which isomer I draw. So there's not 2 possible stereoisomers. There is only 1 possible stereoisomer. Again, no matter how you draw the product, phenyl is cis to one methyl and trans to another. So that's a useful Wittig reagent, a reaction, if you only get 1 product. Let me show you another example. You don't always have substrates that are symmetrical. Let me take an example of another substrate. This one is called methyl vinyl ketone. You're going to see that more coming up in more chapters. Don't you want to add a cuprate reagent to that? I feel like I do, now that you know how to add cuprates and do 1,4 addition reactions. But we're not going to do that here. We're going to do a Wittig reaction. But if we don't want to end up with 2 different stereoisomers here, then we need to pick a reagent where you've got 2 of the same group on the carbon atom of the Wittig reagent. So by doing this, by making sure that these 2 groups are the same on my Wittig reagent, I'm going to end up in another situation where there's not 2 different stereoisomers. I'll draw out the CH2 there, right? No matter what I do, the methyl group is going to be cis to an H and trans to an H. Or the alkene group over here is going to be cis to one H and trans to the, right? So there's only 1 possible stereoisomer. So if, to have useful Wittig reactions that don't give you 2 completely different products, E and Z, you try to craft the reagents, arrange, strategize in the use of the Wittig reaction so you don't get 2 different stereoisomers, because that's kind of a pain. And I want to talk about this P plus C minus thing because it seems kind of mysterious. So again, phosphorus is in the 3rd row. You can have no problem having 5 bonds to phosphorus. It's a 3rd row atom. No problem having, you can have silicon. You can have 6 bonds to silicon. All right, that's crazy. Right, the 2nd row is absolutely beholden to the octet rule. You can't have more than 8 electrons. But the 3rd rows, that's not 2nd row. Okay, let me go ahead and draw one of these Wittig reagents and show the actual bond. So here's the phosphorus atom. And on this phosphorus atom, I have 3 phenyl groups. Not interesting. They're just kind of, well, I don't want to go into the details of why phenyl versus methyl. But so if I take a Wittig reagent, this is the Lewis structure that will help you to understand the reactivity. If I draw P plus and C minus, this helps you because you can see that the carbon atom is nucleophilic. You can see that the carbon atom on this reagent, we call this an ylid when you have a plus and a minus right next to each other. And I can't think right now if you've seen any other ylid functional groups. You'll see some more. There's quite a few, but they might have avoided those up to this point in time. So we refer to this as a phosphonium. That means plus on phosphorus is onium. A phosphonium ylid. So There is another resonance structure that we can draw, and I often draw it because I'm lazy and I don't want to draw the minus and the plus charge. Let me go ahead and draw out that resonance structure. I'll use some arrow pushing and take those lone pairs and attack the phosphorus. This is the same compound. It's just a different resonance representation. And I will allow you to draw this other resonance representation. I'm just scared you're going to forget that the carbon is nucleophilic. So that's why many people will draw the C minus P plus representation. It's because they're afraid that they will forget that the carbon is a powerful nucleophile. So oftentimes I'll write the P double bond C representation. It's the same ylid, even though we don't write the plus and the minus. They're just different ways to represent it. What's the downside here? Right? The downside of drawing this P double bond C, the big downside, is that that pi bond is not very strong. You don't make stable pi bonds to third row atoms. That's second row atoms that form stable C double bond C, C double bond N, C double bond O. That's why on the planet Earth and throughout the universe, you're going to expect to see carbon life forms because you can form stable double bonds to carbon. It's not easy to form stable double bonds to other atoms around the periodic table. It's that second row that's kind of in the sweet spot for making stable pi bonds. All right, where do we get these Wittig reagents from, these ylids? Well, you make them. We have huge jars in every laboratory here of triphenylphosphine. I think that's a blue color, but you get the idea. I accidentally drew blue. Here we go. This is triphenylphosphine, and again, you can buy it in huge bottles. It's used for many different reactions. Somewhere down the line, you're going to make a P double bond O. That's always the driving force. So if we start a synthesis with a trivalent phosphorus with only 3 bonds, somewhere later in your chemistry, maybe 4 reactions later, who knows, you're going to want to drive some reaction by forming P double bond O. Now you use this as a nucleophile in an SN2 reaction, even though it's not a great nucleophile. So let me go ahead and give you a substrate for an SN2, like a primary alkyl iodide. Right? That would be great, right? Not tertiary, something that's good for SN2. You know, this phosphorus is not a great nucleophile. You probably have to heat this to get efficient rates. So even if it's ethyl iodide or methyl iodide, and you guys know how SN2 works. You just displace some sort of a leaving group. Not really the theme of this chapter, but SN2 reactions. And this will initially give you a phosphonium ion with no negative charge. So I've still got those 3 phenyl groups on my phosphorus. But now, since I used its electrons to make a 4th bond, it has to have a positive charge. We call this a phosphonium salt. The X minus is still there. You can't get the X minus away because you need something to balance out the positive charge. Now, to convert this into a phosphonium ylid, we need a powerful base. A super powerful base, and we're only going to teach you one super powerful base in this course that can be used for that. There's others, but we're only going to teach you one that can remove this proton and put that negative charge. At present, from my reaction, there should be 2 H's on there. I'll draw them. And the only reagent we're going to show you is N-butylithium. I'll draw it like this here with all the bonds, but really we usually write it out as N-butylithium. I apologize, that N, the small letter N, should be in italics. The American Chemical Society and IUPAC say, hey, the N has to be in italics. So I'm kind of, it bothers me that I forgot to put that in italics. All right, so that it rips a proton off. Maybe I better draw that. The mechanism is completely uninteresting, right? If you put alkylithiums in the presence of water, they deprotonate the water. And no other base that we show you will be powerful enough to do this efficiently. So, right, N-butylithium, you would almost never use that as a base, but here we need that butylithium to act as a powerful base here. And there's nothing it can attack. You might think it's going to attack the phosphorus to make a 5th bond. No way. Basicity is the key. It's more like it does elimination type processes instead of addition to the P+. And so now you get this, I'll just draw it out the way we normally draw it. Triphenylphosphonium plus, next to this minus carbon here, and there's a lone pair on that. So that's how you make a phosphonium ylid. You do SN2 to make a phosphonium salt, and then in a second step, you deprotonate with butylithium. All right, that's it for today. We'll come back and learn more strategically about the use of Wittig reactions.